fair reciprocal recommendation in matching markets, and our speaker is Yoji Tomita. Thank you for coming to the stage.
Thank you. Hello, everyone. My name is Yoji Tomita from CyberAgent. It's my honor to present my work, Fair Reciprocal Recommendation in Matching Markets, which is joint work with Tomohiko Yokoyama from the University of Tokyo. We consider the reciprocal recommendation systems in two-sided matching markets. Two-sided matching markets, like job recommendation or online dating, is a service that matches two types of users. In two-sided matching markets, reciprocal recommendation systems is crucial for the success of the service. While the standard recommender systems recommend items to users, RRS recommends users to the other side of users. In matching markets, fairness of RRS is practically important. In RRS, individual users are recommended to the other side of users, so unfairness of recommended opportunities directly affects the reputation of the service. So RRS must be made so that users do not feel unfairness about recommended opportunities. However, fair recommendation systems is growing literature now, but I feel fairness of RRS are discussed limitedly in the literature. This is what we did. First, we defined fairness of recommendation opportunities in RRS using envy-freeness notion, which is from the fair division theory in economics and the econ-CS field. And it is introduced in the standard recommender systems literature by Saito and Hawkins recently. Next, based on this envy-freeness notion, we propose a new fair RRS method. In our algorithm, we iteratively and alternately maximize two Nash social welfares by Frank Wolf. Finally, we conducted experiments with synthetic data and real-world data, and we show that there is a trade-off between fairness of recommended opportunities and the number of matches. And our algorithm, NSW, achieves very high level of fairness and the relatively high level of number of matches. Then let's start with the problem settings. As an example, we consider the matching platform of dogs and cats. This example is motivated by a real-world online dating service. In this problem, each user gets k ranked recommendations of opposite users. For example, in recommendation list for dog A, cat Z is on the first rank, and cat X is on the second rank, and cat Y is on the third rank for the dog A's list. This ranked list is personalized to each user. Then users check the recommendation lists and send likes to their favorite users. Dog A sends like to cat Z and cat X in this example. Here we assume the position-based model, PBM, for users' like behaviors. Probability that dog A sends like to cat X equals PAX times VK. Where preference PAX is the preference score of A toward X, which represents how likely dog A prefers cat X, which is computed by some standard recommendation algorithms such as matrix factorization. And function VK is the examination function, like 1 over K. Here, K is X rank on recommendation list for dog A. In this example, cat X is on the second rank, so the k equal 2. Function v is decreasing in k, so that the candidate on the upper position is likely to be examined and get liked by the user. Finally, users who send likes each other are matched. In this example, dog A sends like to cat X, and cat X sends like to dog A. So dog A and cat X are matched. Here, we see the unfairness of recommendation opportunities between dog A and dog B. Dog A is on the first rank for both cat X and cat Y. So in this case, dog A is likely to get many likes from cats and get many matches in this platform. In this case, dog A will feel unfair toward dog A. He will think that it's unfair that dog A is recommended to all cats in the first rank. If he were recommended like A, he would get more likes from cats and get many matches. This is the unfairness of recommended opportunities we consider in this paper. Let's formalize this unfairness of recommended opportunities. Let A be the platform's stochastic recommendation policy for dogs. Aijk is probability that cat J is on the rank K in dog I's recommendation list. Similarly, B is the stochastic recommendation policy for cats. Bjik is the probability dog I is on the rank K in cat J's list. Fix the recommendation policy A and B. We can write the probability of matches between dog I and cat J, like this formula. And we define the social welfare as the expected number of matches. Typically, platforms choose recommendation policies A and B in order to maximize the social welfare, the expected number of matches. Dog I's welfare is the expected number of matches dog I gets, and we write it UI. Here, we note that dog I's welfare depends on his own recommendation list, A, AI ... and how dog I is recommended to cats. It is B.I. Now we can define envy of dogs. We say dog I has envy to the other dog I prime if UI of AI ... B.I. is lower than UI AI ... B.I prime . In words, dog I gets more matches if he were recommended to cats just like dog I prime. In this case, dog I feel unfair toward dog I prime. We say that recommendation policy AB is envy-free for dogs if there is no envies among users, among dogs. Similarly, we can define envy-freeness for cats. Then, how can we obtain fair reciprocal recommendation? In the literature of fair division theory, fair allocation is obtained via Nash social welfare. It is the product of the agent utilities. In our setting, we can define two Nash social welfares for dogs and for cats separately. Nash social welfare for dogs is defined as the product of all dog utilities. And then we say that recommendation policy for cats B star is NSW best for given A if B star maximizes the dog's Nash social welfare. Similarly, we define the Nash social welfare for cats as the product of all cat utilities, and we say that recommendation policy for dogs A star is NSW best for given B if it maximizes cat's national social welfare. This NSW best recommendation is what we want. this is theoretical guarantee of fairness of NSW-based recommendation policy. For k equals 1, if A star B star is NSW-based for each other, then A star B star is envy-free for both sides. And for the case of k is larger than 1, with weak conditions, NSW-based recommendation A star B star is approximately envy-free for both sides. Then, how can we obtain the NSW-based recommendation? We propose an alternating maximization of two NSWs via Frank-Wolf algorithm. Intuitively, this algorithm iterates convex optimization of log NSW2 and log NSW1 alternately. First, initialize A and B, and repeat the following update. Update A for increasing direction of log NSW2, and update B for increasing direction of log NSW1. After convergence, we can obtain almost NSW-based recommendation. Finally, I explain the experimental results. This is experimental results with synthetic data. We generate preference scores, Pij and Pji, and the parameter lambda controls the level of popularity or diversity of preference. Large lambda means that all dogs like a few superstar cats. Examination functions are vk equals 1 over k and log of 1 over k plus 1. Comparing methods are some practical or recently researched RRS, like naive, plot, TU matching, and others. And SW is a heuristical algorithm that aims to maximize social welfare, the expected number of matches, and NSW we propose. As a result, the upper graph represents the expected number of matches, and NSW is the yellow line. And we show that the NSW achieves relatively high level of expected matches. And the lower is the number of envies among users. And we show that NSW achieves almost 0 envies. So NSW is much fairer than any other methods. Finally, this is a real-world data experiment. We use our data from Japanese online dating service. And this service has huge size of active users, so we sampled about 200 men and 200 women. Preference scores are computed by matrix factorization from like and match data. Here we show that NSW achieves relatively high matches and almost 0 envies among users. This is summary. Thank you very much.
Thank you. There are several questions in the chat. So one is, high envy is bad because a user wants others' items, but envy might be low if a user is atypical and gets bad recommendation, but doesn't like the peers' recommendations. Would that be a problem for your definition of fairness?
Sorry?
Would it be a problem for your definition of fairness if envy is low because a user is atypical and gets bad recommendation because of that, but also doesn't like the recommendations of the others? Yeah, maybe you can check out the questions in the chat. There are several interesting questions in the chat, but we are already at the end of our time. So let's thank again the speaker.
Thank you.